more about it, any components of this center. He's been author of numerous publications in earthquake engineering, strong ground motion, and health monitoring. And he's been very active in committees promoting new technologies for the control and prevention of earthquake disasters. So please, welcome.
Thank you very much for the kind introduction. Yeah, I came here in California to attend the AGU conference from next Monday. So I gave an invited lecture about the earthquake early warning system having a structural health monitoring function. So taking advantage of my trip to California, I'm happy to be here to give almost one hour lecture, less than 1 hour lecture regarding this title. So you can see this is the 1 million city, Sendai. We are now expecting next Miyagi earthquake, subduction zone earthquake. So in 10 years, the occurrence probability is 90% already. And in 20 years, 93. In 30 years, almost 100%. That means we must prepare earthquake early warning, countermeasures against earthquake. And for a subduction zone earthquake, we have the certain time to prepare quick reaction using a warning system. So one of my recent activity is focused on that kind of field. So here we are Sendai. Sendai is the central city of Tohoku district in the 160 kilometers north of Tokyo and 1 million population. And here is Sendai. And today I talk about at first background of the approaching Miyagi earthquake and the use of online waveform data. Then I talk about the basic conception of the earthquake early warning system with the structural health monitoring function. And I talk about the characteristics of the national system. From the October of 2007, we started actual practice of the earthquake early warning system in Japan. But we have some limitation of the current warning system. I talk about the detail later. Then I talk about the outline of the developed system, and then the example of the online health monitoring system of a 9-story RC system, exactly speaking, not SRC, RC building. And the next I talk about accurate ground motion prediction using a front side waveform data. Okay, we can use the online. We can apply, sophisticated technology, transmission technology from the front side near the source. Then the continuous data transmission, waveform data. Every 2 seconds, 0.2 second packet, 100 Hz sampling data is coming. And what can we do before we get such kind of data? Okay, we are now trying to such kind of ground motion forecasting using front side waveform data. And today I talk about the investigation using artificial neural network. We are now trying to a different methodology. This is one of the PhD doctor's thesis written by the Turkish student. He now works for Sakarya University in Turkey. So then not only PGA and PGB, we can now succeeded to predict the Fourier spectra. So that means the before arrival severe shaking, we can predict, Fourier spectra with a high accuracy. That make it possible to become a bridge of the structural control and the engineering seismology in the near future. Feed-forward control can become available, I think, not feedback structural control. So reference, as for the reference, I can show the Motosaka et al. This is the development of the our system. This is the published to the AIJ technology and design, and about the health monitoring based on the continuous observation data. Recent last year's Iwate Miyagi Nairik earthquake data we introduced in this conference, and this is the 1940 years continuous data. No, same building, just after completion of this building, and including before and after the retrofit. And in 1978, last Miyagi Oki earthquake shaked severely at the 9th floor, so maximum acceleration record exceeded 1G, 1,040 gal at the 9th floor, and severely damaged. Then in 2000 and 2001, we retrofitted, and the dynamic characteristics has been changed. Okay, and the real-time ground motion prediction using front-side data, Kuyuk and Motosaka. This is the Journal of Disaster Research. Maybe I handed out the reprint of the paper. And also we published the paper at the 14th World Conference and the Japan Association Earthquake Engineering. This is Journal of JAE, and we already succeeded for the prediction of spectral forecasting of ground motion with information of earthquake early warning systems for structural control. Okay, this is the background, and this is my introduction myself by television introduction. Sorry, Japanese.
地盤の振動、揺れと、それから波がどう伝わるかと、地盤の波の伝わり、こういうのを専門にしております。
東北大学災害制御研究センター本坂正人教授、地盤と構造物のプロフェッショナルである本坂教授は、地域の地震災害軽減を目的とした研究を進めています。
最近力入れてるのが、この大揺れの前に警報を出すという地震早期警報システムですね。気象庁からこの地震ですよ。
Some English translation is not so good.
それをこの一般市民にどういうふうに伝達して地震時の人的物的被害の低減に結びつけていくか、こういった研究をやっております。
これは訓練です。
This system is installed to the school elementary
新幹線
school.
直後に大きな揺れの到達時刻や震度を推定し素早く知らせる緊急地震速報。本坂教授はこの速報を高度利用できるように研究を進めています。
仙台の各地点の揺れの成分がどれぐらい、でどこがどういうふうに揺れるのか、こういうのが即時に分かるような予測技術の今研究やっています。
本坂教授の研究グループは仙台から東に60キロ離れた石巻市押鹿町の総合支所に地震計をセット。宮城県沖で発生した地震をいち早くキャッチするシステムを構築しています。押鹿総合支所で観測した揺れのデータは瞬時に仙台市にある本坂教授の研究室に送られます。地震計に振動を伝えてみると
1、2、3、はい、もう一度1、2、3してますね。
リアルタイムデータトランスミッション。
1、2、3で叩いて、そしたら波がこう来た。それで私は音聞こえてる、床叩いた。向こうの音が携帯が遅れて、まあほとんど同時に。国の地震計、緊急地震速報も含めて高度利用、独自の地震観測も合わせてですね、高度利用することによって危険度に調和した対策やっていくっていうのが一番効率的な。宮城県地震、お金はない、自治体もお金ない時に、時間もないという時に、もうちょっときめ細かな情報をですね、大学が絡んで提供していくっていうのが大事なんじゃないかと、こういうふうに思います。
This is a 9-channel data from the 60 kilometer far from. And this kind of demonstration was done in the Istanbul 2 months ago. From Tokyo and the Istanbul, we showed this kind of. Sorry. Okay. Now I just briefly talk about our earthquake background. In the subduction zone of Miyagi offshore area, we have there every about 40 years magnitude 7.5 earthquakes occurred. So last earthquake was occurred in 1978, and already 31 years passed from the last earthquake. Average is 37.1 year. That means the very high occurrence probability. Then already, part of the expected fault area was actually slipped in the 2005. 1/10 of the earthquake energy is released already. So this data also provide many important information for us. No way to use this kind of information data. When the fault plane slipped, what kind of ground motion is expected by using front site data. This is the Oshika site. First observation site who get where we can get the observation data. Then we can transfer the real-time ground motion to Sendai. And before arrival S-wave, 15-second time delay we have. But no time delay data transmission. In that situation, what we can do? That's my our question. And we have so far many research topic regarding this kind of warning system. And in introduction, I talk about the national system briefly. So within all over the Japan, we have the about 1,000 seismometer, 800 from the NID, National Institute of the Earth, and the KNET, yes, KNET, and KNET is not exactly the FNET is used for, HiNet is used for. KNET and HICNET is the now not used for the warning system, but other 200 observation system in the the JMA, and total 1,000 seismological data is used. But these real-time observation data is used to determine only a point source. Source determination only. Even if large scale earthquake, I mean the 7.5 class earthquake has a dimension of 40 multiply 80 kilometer dimension, but point source is not enough, and the conventional attenuation formula is not enough to predict the precise ground motion characteristics. That's why we feel such kind of limitation. So when the earthquake occurs, there are observation system getting waveform data, so we can use directly waveform, not backward, but the forward use of ground motion. This is my idea. And this is the national system. 5% magnitude is used, and before S wave arrival, seismic intensity and arrival time are estimated. And the warning alarm for human reaction and the mechanical reaction is done. Okay, this kind of. But the limitation I already explained. Difficulty in the applicability for near source earthquakes and the coastal area for subduction zone earthquake. But the limitation and the limitation of immediacy due to one ramp and concentrative data processing. And the earthquake observation information is used only for determining source information. This is backward use. And the system environment is not available for forward use. So if the JMA and NID provide the all time history data to the research institute or the other organization, but the current hardware is not possible. Many reasons. But the only for a certain area, like a Sendai area, university can do such kind of data collection by using our own system. Okay, and then the also we can use the combine the national data and our own data. That's nothing else, the integrated system. So based on these limitations, necessity for improving immediacy and redundancy must be realized, and the forward use of the independent observation network would be promoted. Not only the on-site warning system, the local, regional system may be realized between the national system and on-site. That's my idea. And the highly accurate ground motion prediction can be done. So this is an illustrative figure to explain the backward use and the forward use. Now our current system is, for example, this is the first observation point. Then the backward to point source, then the conventional. This way has a limitation, even if many data has been used. So why waveform data is not used or are not used? This is this is the forward idea of forward use of front side waveform information. Okay, at the front side, if we get the data continuously, we can set the data, and we can get the data here to evaluate the real-time ground motion. The observation point is observation motion is directly used as the input data to prepare the system based on the past observation data. For example, using artificial neural network or other method to model the ground motion, real-time ground motion prediction. And now I talk about the development of the warning system has the structural health monitoring system. Basic conception is monitoring function as a daily function. Warning system requires daily maintenance. If warning system has not daily function, that's very how do you say, not good for economical viewpoint, because the earthquake occurrence is very few, not daily work, once per 2 years or So every day we must pay a communication fee and a maintenance fee. So no way to add the daily function. The one of daily function is the structural health monitoring, and we can get the some every 1 hour or every day's same time sampling or seasonal sampling. So many kind of daily usual data can be obtained by using this kind of system. Of course, event sampling is very important. From the small earthquake to large earthquake, and they are available from micro tremor to strong motion, and for investigating amplitude dependency. So a sensor with a dynamic range would be needed. About at least 100 dB class, sensor would be needed. We used the 120 dB class, that wide dynamic range. Now, sensor price become cheap compared to the 10 years. A micro electromechanics sensor, MEMS sensor, with the 120 dB is about the $1,600 US, such kind of less than $2,000. Yes, and the fixed time sampling and the event sampling, and the not only P-wave detection at the front side, and the online data transmission successfully to the center. This lead to the available sampling and the variable sampling and the variable packet length. This kind of technique is needed. Now our system is up to 1 kilohertz sampling. And the packet length, minimum packet length is 0.1 second. So normally we use the 0.2 second packet and 100 hertz sampling. So every 20 data for every 0.2 second is coming. So a 9-channel data means the 180 data every 0.2. That means the 9-channel data can be transferred by using ADSL line. Not possible in the ISDN line, but the ADSL line make it possible. And the same system on the evaluation side to enhance the applicability near source near source earthquake. So on-site warning can be available, okay, if we install the same system. Then the make and transmit P-wave detection information at the front side. Warning from a JMA P-wave detection information on site. This kind of warning information can be made. And not only seismic intensity, but also PGA, PGB, spectral, and the possibly the waveform has more accurate information. And the information processing using, a band pass filter make it possible as the, applicable for the some specific height of the building, or the and utilized for the feed forward control of the active and semi-active structure control. And not only information before S wave arrival, but also the during S wave, and the information of shaking termination can also be issued. Okay. And the connection to structural analysis immediately after the ground motion shaking. And maybe the 1 minute later, we can identify what column is mostly damaged, what beam is mostly damaged. We can identify by connecting the structural analysis just after the earthquake termination. So actually developed system applicable to near source earthquake and the use of front side waveform information and the development of accurate ground motion prediction. So when the earthquake occurred here, we can get the observation data here. Then the real-time transmission make it possible to predict the PGA, PGB spectra, possibly waveform in the near future, by adding, site information, waveform, and source information as their point source. Even if rough information, source information should be used, because the when earthquake occurs this direction, we cannot use, no way to use this one. Okay, so for Miyagi earthquake, we are now using this front side data. This physically another observation point, and the between the Sendai and the Oshika, we also installed the another observation point. So these observation point make it possible to transfer the real-time data. And what can we do using such kind of data? We are now trying to. And this is the our. This is Oshika. Photo is opposite. This is Oshika building. This is a 9-story building. 40 years continuous observation has been done. Now I can show the data. Then these data are coming through the internet. And in our center, we have the national earthquake early warning system from internet, and this data is coming and the processed using to predict the precise ground motion prediction. And what can we make the structural health monitoring information along the time series? What can we issue ordinary times? And what can we issue before shaking them? And what can we issue during shaking? And what can we issue just after the earthquake? Okay, so not only before, during, and after. Now, if the Oshika, ground motion is finished, we can announce in the 30 seconds later, ground motion will be stopped. Okay, this kind of announce can be issued. And we can combine to the structural analysis. And this is the example. This is the earthquake occurred Miyagi Oki area. And this is the Oshika's waveform data. P arrival here, S arrival here, and the Sendai in the P arrival here, and S arrival here. Okay, about 15 seconds exists PS time. And after P wave arrival, Oshika, this PS time, Oshika's P and Sendai's S, about 20 seconds. Okay, considering their process time to determine the earthquake source and the other calculation of the seismic intensity, such kind of data processing lead to about 4 seconds. That means at more than 15 seconds exist before arrival S wave, even if we use the.
So how far is the earthquake?
Earthquake is the Miyagi Oki earthquake is here, 100 to 120 epicenter distance.
From the front side or from Sendai?
From Sendai, yes. Front side is 40 kilo, 40 to 50.
And so you get P minus S arrival of, you said 15 seconds?
Yes, here. This is P minus S, and this is Oshika's P minus S. And if we catch the P wave here, and when we get the warning alarm from JMA, we already get the 5 seconds of P wave data in Sendai to Sendai. And the source information from JMA and the P wave form data from front side. Only 5 second P wave data. But this is very important, Okay, even if the P wave.
This depends where the earthquake is. This is a subduction zone.
Subduction zone, yes.
So if Miyagi Ken was far out, not so deep, but the subduction zone can have a slip at the depth, so the distances would be totally different. And the time. No. This area is about along this point, depth is 60 kilo. So this area is about yes, about 6,
shallow.
0.
Okay, 40 to 20,
What is the depth under Sendai.
Here,
Yes,
depth.
yes.
Depth is here. It's very deep.
120.
100. Yes.
Something like
This is depth. Subduction zone is here. Miyagi earthquake characteristics. One of characteristics is fault area. Asperity location is fixed, already determined. This is a very rare place. Of course, there is another such kind of region where the focal area is specified, can be specified. Then this is the online waveform data. This is the Oshika's data. First 3 channels is the 3rd floor, the 2nd floor, and the 1st floor. Now I can show the real-time ground motion here by internet, but no time to present. But if we have a network, we can show real-time ground motion. And also we can show the running Fourier spectra like this. And now I talk about the example of the structural health monitoring at the our building. This building was completed at the 1968, just 40 years. And the 1978 Miyagi Oki earthquake at the 9th floor, 1G record was observed, and the retrofit work was done in the 2000. Then the amplitude-dependent natural period has been investigated based on the continuous observation for 3 months, including last year's Iwate Miyagi earthquake. This is the inland earthquake, not Miyagi earthquake, but we get here continuous data before and after, from micro tremor to strong motion. Then the sensor is the 1st floor, 5th floor, and 7th floor. And this is a MEMS sensor. This is the strong motion meter of the BRI.
Is this the old-fashioned paper recorder SMAC?
This SMAC is the old-fashioned.
Yeah. Okay.
Yes. This is a new one, our. And the data 5 minutes data it's analyzed for to identify the first natural frequency in the every hour. Then the stiffness reduction ratio is calculated by the peak frequency. Then we can determine the damage index proposed by the Wan et al. This is used for the Taiwan or California.
This is not the building. This is substructure interaction.
Yeah,
It's not the damage indicator. This can be all in soil.
yeah. This is the soil is of course.
It's the system frequency.
Yeah, yeah. But the interaction effect is not so large in this building. So damage. So this is the 3 months data. This is the July 14th earthquake. This is the transversal direction data. Natural frequency is changed here. Okay, and this is the natural frequency at the stage of the maximum acceleration point, about the 0.4 G, 0.4 G. And the systematically changed here. And the okay, so before and after, micro tremor level dominant period changed, in the 7.3%, reduction. Okay, and the in the 5 days, stiffness recovered a bit. First 5 days. This is very interesting. Okay, and the compared to the small amplitude, at the during a strong motion, stiffness reduction ratio is about 50%, 1/2. Then during there is another earthquake. This is Iwate Engan Hokubu. This is a intraplate earthquake. This is the Ibaragi Prefecture earthquake. Maximum acceleration is here. So, but not changed here. Also here, during Iwate Miyagi earthquake, natural period change. This means during that earthquake, new crack would be produced, generated.
What happened after 6 months?
No?
What was the thickness after 6 months?
This,
You had
this is a microtremor.
no, yeah, I understand, but these are days here, so you have like
That is.
maybe 1 month.
This is 3 months.
Where?
May 1st. This is July 1st.
No, I mean 3 months after the right end of the ground.
3 months after.
Yes.
No change.
Stays the same.
Yeah,
level.
same. And the
The building is on a hill, actually.
on the hill, yes.
It's not
Not bad.
flat.
And the this is the amplitude dependent dynamic character, change of natural period 40 years since completion. This is the deflection angle, deflection divided by height. This is 100. So that means the height is about 30 meters, 9 story, 31. And the before 1978 earthquake, this line. Okay, then after Miyagi earthquake, going down this line, along this line, and due to a retrofit work, dynamic stiffness, natural period moves along this one. And the last earthquake, July last year's earthquake, was the largest along this one. Okay, this is a transverse direction. This is longitudinal direction. This is 40 years continuous data.
But this is still telling you that the change in the building is a small fraction of the change due to the soil. Because the change in the building is like 0.1, let us say. And due to the soil, to the rocking angle, it is like
Yes, this is rocking
like
effect.
0.5, 5 times more change.
Yeah.
4 times more change.
This is due to a severe crack, not soil. This is the
No, I mean the trend, the whole trend.
yeah, whole trend. This is the this is the severe due to major trend is due to crack, deterioration of the concrete stiffness. And the real-time monitoring for during earthquake can be used the Kalman filter like that. Then we can identify the stiffness ratio versus the deflection angle. This kind of figure can be identified using many data.
What is SRR?
Stiffness reduction ratio. Okay. Then I talk about the accurate ground motion prediction using front sight. So using waveform data from front sight, what can we predict PGA and PGB? So we use the 39 KNet database for Miyagi earthquake, and these Oshika's P-wave data is used to predict the Ishinomaki and Taiwan and Shiogama and Sendai's ground motion prediction by using 39 earthquake data set. So using P-wave form, Nakamura Yutaka-san used the this kind of velocity divided by this kind of factor is used dominant frequency, and the Kanamori and Wu used the tau c using P-wave data, and I use the linear combination of sine wave, sinusoidal wave. Then we can use the amplitude and the frequency and the phase, initial portion of the P wave. This kind of data can be used to predict. This is the fitting of initial part. This is online fitting. No need to take time. Then the ANN structure has been made. Local location and magnitude coming from and waveform information from front sight and site information. These are from national system, and these are from our regional system. Then they combine the information. Then the PGA and the PGB. Then this is a conventional prediction. This is a predicted one. This is an observed one. So our system lead to the drastic, enhancement of the accuracy. And this is a velocity. So I must say the using 98 earthquake data, 35 data are used for learning of ANN structure.
What is the scale?
Scale is the this is a kind, a centimeter per second. This is a centimeter second. Yes, this is.
It's based on Gauss.
Yeah, acceleration is Gauss. Yes.
That's kind of small.
Yes, this is large. Yes, this is a small one. Yes. So largest one is the here. This is 100 to.
For the velocity.
Velocity is yes 10 to 20.
Centimeters per second.
Yes, 20 centimeters per second. This is not so small.
Meter.
Mm.
Meter is
No,
strong.
not meters.
We can go
Cannot
high.
be meters.
We can go to,
Centimeters.
Centimeters.
we can go to 300 centimeters
Yeah,
per second.
yeah. So 300 would be larger square.
Yeah,
Yes,
very,
yes.
very large. I teach you that.
Yeah. And this is the statistical result. Drastic improvement has been done. And for spectral ground motion prediction, we apply the 40 interval from the 0.1 Hz to 10 Hz. Then the same kind of ANN structure has been made, and the same data set can be used. Then the training data fit the almost the same, exactly almost same, and the testing data, very nice, coincidence will be recognized. So if we get this kind of, ground motion prediction before arrival S wave, we can, for example, this is Kajima's, for example, AVS system. What kind of stiffness type would be most appropriate before arrival? Then for 2005 August earthquake, at the different foresight, most appropriate stiffness type is shown here. And if we compare the different earthquake, even if the same site, if the ground earthquake source is different, different structure time is identified. Okay, this means depending on the incoming waveform, we can adjust the appropriate stiffness. This kind of control can be done if we precisely predict the coming earthquake ground motion. So now I come to the summary and concluding remarks. I first talked about the development of earthquake early warning and the structural health monitoring system. And I explained the conception and system configuration and examples of observation record. Then the examples of online health monitoring of our existing 9-story building is introduced for the last year's data, and also the 40 years continuous observation data, and the amplitude dependent dynamic characteristics has been discussed. And accurate real-time ground motion prediction using front side waveform data it's explained for the method using artificial neural network, and the examples are shown. And contribution to the advanced engineering application, such as feed-forward control of structural health, structural vibration. This kind of work can be combined with this our forward forecasting ground motion technology in the near future. Maybe in the near future, time history or response envelope like non-stationarity can be predicted. So what kind of ground motion it's important. This should be discussed with the structure control person, and what kind of observation point would be fixed as the front side. Okay, and okay, so this is my presentation. Thank you very much for your attention.
Questions? Yes, and I have many actually.
Good question. In Sendai, what are the major sources of earthquake? Only subductions, or you have intraplates, or you have other faults?
Now we have lots of earthquake type. Most possible earthquake is the subduction zone earthquake, highest in the world. Okay, Miyagi Oki earthquake. But even if subduction zone, we have the two types. One is the plate boundary type, and the other is the intraplate type. And the other type is the inland earthquake, cluster earthquake. This can be occurred. And the Iwate Miyagi earthquake was one of them. So 120 kilometer north, that was caused in the cluster, active fault. And just near the Sendai, below the Sendai, Nagamachi Reef active fault we have. So such kind of near source ground motion, inland earthquake also occurred. In the earthquake damage prediction of the Sendai city, I'm head of the project, of the damage prediction project. And all earthquake environment, we have taken into account. But for subduction zone earthquake, most important. Of course, we extend 160 degree. But now these 3 years and this fiscal year and the next fiscal year, we focused on the subduction zone earthquake.
I have some comments.
Mm-hmm.
What you call first motion type of forward analysis.
Mm-hmm.
I just want to comment that
Mm.
the theory for real-time forward inversion of the source exists for the last 30 years.
Mm-hmm.
However, it is very difficult to apply in your case
Mm-hmm.
because you have stations on land.
Mm-hmm.
And so statistically,
Mm-hmm.
I don't know, 90% of time the earthquake is here, the stations are there.
Mhm.
You don't have stations around the source, so the
Mhm.
uncertainty is huge.
Mm-hmm.
So it's very difficult to predict with certainty the real-time, real inversion data.
Mm-hmm.
But the theory is perfectly available. The other thing is that it's very difficult to do that in 10, 15 seconds.
Mm-hmm.
Because it's a generalized inverse approach with a lot of models and
Mm-hmm.
maybe some Monte Carlo simulation takes
Mhm,
a lot of
mhm,
time. So
mm.
maybe you need another generation of computers, but you can do it.
Mm-hmm. But the difficulty, yes, of course, your suggestion I understand. But if we have many data, past data, and incoming, some data, real data, then what can we do?
Well, you can, seismologists will tell you right away that you can use the empirical Green's function approach.
Mm-hmm.
But some of us engineers don't believe that works very well. But, what I'm saying is that the computer programs exist, and they're very good today.
Mm-hmm.
But running the calculations so fast is not feasible in 50 seconds. That's
So without having forward,
around the source.
yeah.
Yeah.
But way of thinking using a front side waveform data, this may lead to the more accurate.
Yeah, definitely.
Yeah.
Definitely.
Constraint condition as become constraint condition better than go back to to determine the only point source.
No. I'm not talking about. I'm talking about the full source inversion. You will tell that it started here when this.
Yeah.
Started here is present.
Yeah.
I'm talking about the complete inversion.
Yeah.
That is very computer intensive.
Yeah, but we are now discussing our early warning system. So if we try to complete source inversion, this is physically impossible because rupture velocity is slower than S wave.
It's about 2.5 kilometers.
But